Okay, hi everyone. Thank you for being here. This is another Sam Salmon exclusive. Today, Christian Mendoza, the editor-in-chief, and I, Mr. Brian Dormeyer, are really excited to interview Dr. Josh Schlieder, who is from NASA. I have a little bit of information about Dr. Schlieder. He is an astrophysicist, works at NASA. He works primarily at the Goddard Space Flight Center in Maryland. And I believe his focus, and he can correct me if I'm wrong, is on exoplanets, which from what I know about exoskeletons, these are planets that are outside of our solar system is what I'm guessing. Okay, thank you. In our research, Christian and I, Dr. Schlieder, we noticed that you had three, I think, areas where you do a lot of work. Could you talk just for a minute before Christian speaks or asks the question about the TESS satellite? Because I know that's something you work with. Also, the Nancy Grace Roman Space Telescope, which is something that's coming up here in a few years. I think you've done some work at the Swift Observatory as well. Could you tell the audience what these things are?
Yeah, sure, I can. First off, the TESS satellite is a NASA astrophysics mission. It launched in 2018, and it is what we call a medium-sized explorer mission. This is a kind of mission where people in the community, the astrophysics community, it's an open call. They submit proposals and say, we want to build a mission to do this science that's underneath sort of the astrophysics themes within NASA. And they're reviewed very rigorously by a panel. And then a mission is eventually selected for implementation. That's what the fancy word we call it, which means to build it and fly it and get science. And so TESS was selected and built and launched in 2018. And the focus of the TESS mission is to find exoplanets via the transit method around nearby and bright stars, which means that if you find a planet around a nearby and bright star, it is much more available for deeper characterization to understand its mass, to understand what may be in its atmosphere and other sort of second level properties of that planet. And the way TESS does this is pretty simple. The satellite carries four telescopes that are sort of aligned, so they add up to cover a very big piece of the sky in one shot. And it consistently just takes images, and you extract from those images the brightness of the stars, and you look at the brightness as a function of time, and you look for small dips in the brightness that are characteristic of if you have a star, and in our line of sight, the planet orbits around and goes in front. When it blocks out the light, you see a dip. And then when it comes around again, you see a dip that looks the same. You can measure the period, and the dip is characteristic of the radius of the planet. And so that's what TESS does. It's an exoplanet discovery mission. And it's been going since 2018. It's doing very well. We found more than 2,000 planet candidates at this point in the mission. And more than 100 of those 2,000 or so candidates have currently been sort of confirmed to be a real planet. They're not noise in the data. They're not some other astrophysical source. They are a planet orbiting a nearby bright star. And we're off to the races, so to speak, to characterize those planets in detail and really learn about them now.
Thank you. Yeah, much of my knowledge of planets took place in a shoebox in 7th grade. But I know Christian had a question about TESS in these planets that have been found. Christian, it's a great opportunity for you to ask that question.
Yeah, so you explained how TESS works. So let's say some alien species uses that same exact method and looks over to our solar system. What information can they find from that?
That's a really interesting question. And there's actually been, I don't know if the paper ever got published, but I knew some people who were doing work to sort of figure this out and say, well, you know, we're looking for planets crossing in front of their stars from our line of sight. And who out there, if anyone is out there, could see the Earth crossing in front of the sun and sort of detect us in the same way. And it turns out that there are stars out there that are aligned properly where you could make this measurement. Whether or not there's any life or intelligent life or anything, that's a completely open question. But what we have to keep in mind is that the transit method requires extremely high precision measurements of the brightness of stars, because when a planet passes in front, the change in brightness is very small. It's fractions of a percent. And so you have to monitor with very high precision for a very long period of time. And typically we need to see at least 3 of these dips in a periodic way to claim that there's a planet candidate there and really go after it to confirm it. So if you're going to observe the sun from some distant system that's lined up the right way, you need to have really high precision measurements for a period of at least 3 years, so we can see the Earth cross in front of the sun 3 times. And if you have that, and you also characterize the sun, and you know the sun's size and temperature, et cetera, you do get some information. First, you'll know the size of the planet. We could say the size of the Earth because the depth of that dip in the light curve is consistent with the ratio of the stellar size to the planet size. So you can, if you know the radius of the star, you know the depth of the dip, you can get the size of the planet. So number one, we can figure out how big the Earth is. That's an interesting thing. We get the period, and if you know the period of the planet and you know how bright the star is, its luminosity, you can estimate the temperature of the planet also. And so you could say, okay, this is a pretty small planet compared to Jupiter and Neptune and things like that, if whoever is looking has that in their solar system as well, which tells us it's likely rocky because it's really hard to make a gaseous planet, you know, that's small. And you could tell the temperature. You know, this is sort of an estimate of the temperature because it's really dependent on the atmosphere and other things. But, you know, we can estimate that it would be of order the right temperature to be conducive to liquid water, which is sort of what we're really after when we're looking and thinking about habitability, which is a very complicated and complex question. But the transit measurement that some other, you know, people elsewhere could make could tell you those 2 things. And that's effectively what we know about these kinds of planets from missions like TESS and before TESS, Kepler.
Okay, awesome. Christian, do you have anything else about TESS? I think you had a few there that you wanted to ask.
Well, yeah. As of today, there are just more than 4,300 exoplanets that have been discovered. How many of these planets do you think contain life?
Yeah. So the question of exoplanet habitability is a prime question, and it's a very difficult question. I would say, you know, to ask you a question, what kind of life are you talking about? Do you mean simple bacterial life? Do you mean, you know, small multicellular life? Or are you talking about things that, you know, are effectively reaching our level of intelligence? These are the kinds of things we have to consider when you say, does a planet, you know, have the right conditions to potentially support life? And so, you know, I'll tell you what we know. We know that in this sample of more than 4,000 exoplanets that have been identified, some fraction of them, it's not a whole lot, but it's not a tiny number. There's not just 1 or 2. There's numbers of planets that fit the description of a planet that's likely small enough to be rocky, which therefore has a surface, which is kind of a requirement for life as we know it. There may be exotic things like life in atmospheres, et cetera, but we'll focus on things with a surface. And they orbit their host star with a period that corresponds to some distance from the host star, where we can estimate their temperature, and that estimate would be consistent with, if all else is equal to the Earth, having liquid water stable on the surface. And so if you have a surface and you can be the right temperature to potentially host liquid water, those things are what we know are important for life. And so that's sort of where it stands with these planets. We know their size, we know their orbital period, we have an estimate of their temperature if you make some assumptions about their surface and their atmosphere. And, you know, I don't know the exact number of planets that fall into that category out of the sample of more than 4,000, but it's probably dozens, I would say, at this point.
Okay.
So, you know, that is what we know. And getting to the next level of that question, saying, well, does the planet have an atmosphere? And if it does, is it the kind of atmosphere that would be appropriate, where it's not going to be a very crushing high pressure atmosphere like Venus, or have a very thin, tenuous atmosphere like Mars? That's sort of the next step that we're after. And there are observatories in space now that are starting to pursue this, like the Hubble Space Telescope, that can take very detailed measurements of the spectrum of a planet while transiting. And there's an upcoming telescope that you may have heard of called the James Webb Space Telescope that will be launched later this year. That's sort of the next step in that direction, with a bigger mirror, higher sensitivity instruments to really start pushing into measuring the atmospheres of small planets. But even then, if you have a small planet, the right separation from the star, and you say, oh, wow, we detected a signal that's consistent with some kind of atmosphere, that still doesn't guarantee you that it has a habitable climate. There's a lot more that you need to know, and then the race is on to learn more about the planet. And so how many might host life? Being a scientist and telling you the truth, I can't answer that question. But I can tell you that there are planets out there that the information we currently have in hand does not disqualify them. And we're trying to learn more about them to really solidify the next step in information, see what it tells us, whittle down the list of candidates, and then move on to getting more measurements in the future to really bring that in. And I'll also say, as a final point, the star matters also. Star like the sun is sort of middle-aged, pretty inactive. It's not belching out enormous, flares all the time and damaging particles that would really hurt a planet. But not all stars are like that. And we have to be cognizant of what the star is doing to the planet as well. And that planet might look really good in and of itself, but then when you look at what the star is doing, you say, wow, that this radiation environment is going to be a struggle. So there's a lot that goes into habitability, and I hope my answer wasn't too disappointing, but that's where we currently stand on the topic.
All right. Yeah, that's really interesting. So let's say you do find an exoplanet that has life on it. What would be the first thing that you would do after this discovery?
Well, I think, if I was involved in that discovery, it would be sort of a time to really reflect on where we stand with our perspective as humans living on this planet in this galaxy, in this universe. I think it would be a super interesting sort of turning point in the way that we see ourselves. It's going to depend on individual perspective and people's backgrounds. But, it's going to be a change if we get to that point sometime in the future where we have rock solid evidence that out there, this planet around this star seems to show indications of some kind of life. I mean, that's going to be pretty incredible. The truth is as a scientist, if we ever get there, we'll probably just move on to the next one and think about what to do next. I think ultimately in the far future, sending robotic probes to investigate that kind of planet up close would be amazing, but that's a technological leap that we don't have yet. We got to find the planets first. So that's what we're working on.
Is there any danger in satellites from other countries? I know that sounds crazy, but recently a Chinese satellite came crashing to Earth and I was fixated on it. I don't think other countries have the same standard that the United States does and NASA has. Do you ever worry that there would be some sort of collision in space, or something would happen to these other satellites?
It's a good question, and other countries have standards, and we partner with a lot of foreign countries on different missions and satellites all across the agency. Okay. And the reality is that when you send things up into space, into low Earth orbit around our planet, they do eventually come back. Most of them come back. And we do have standards in place for reentry and things like that, but it's not always perfect, and sometimes things go wrong, or sometimes things are overlooked. And the reality is that as space gets more crowded, and we're launching more and more satellites, and more people are getting involved, both in different governments, different agencies, and in the commercial market, which is really, really growing at this point. There's going to be more satellites up there, and the likelihood of collisions or space debris will increase just statistically because there's more stuff. But I will tell you that we're very cognizant of this. There are methods in place to track and keep track of all these things. And the reason that we knew that this piece of debris that you had mentioned was coming in is because it was tracked, and we pay attention to these things. And it will be an ongoing concern, and is a concern, and we'll keep doing the monitoring and developing our systems to keep up with the demand. is what I would say.
Thank you. Christian, let's transition to talk a little bit about the telescope. Do you want to ask about that?
Yeah, so the Nancy Grace Roman Space Telescope
Oh,
is,
yeah.
It's an infrared telescope currently under development. What do you expect this telescope to achieve, and why is this necessary?
Sure. So Nancy Grace Roman Space Telescope is going to be the next large, what we call flagship mission to come after the James Webb Space Telescope that, as I said, is going to launch later this year. And this telescope that we refer to as Roman is going to be the same diameter mirror as the Hubble Space Telescope. But as you mentioned, it focuses on infrared science. And what sets it apart from Hubble is that the field of view is much larger. So if you compare the field of view of the Roman imaging camera to Hubble, it's about a factor of 100 larger. So you cover 100 times more sky in each image. So picture the beautiful images that have come out of Hubble of all different kinds of sources out there in the universe and in our own galaxy. But instead of, every image being focused on just one object, you're covering 100 times more sky in every image with comparable sensitivity, comparable resolution. And why we need that to achieve new science with Roman is because it is truly a survey telescope. And so it's not designed to just look at individual objects with a small field of view. It's designed to have a big field of view, survey large portions of the sky, and detect very large numbers of objects. And it has two sort of primary science approaches. The first one is to study dark energy and sort of the history of the formation of structure in our universe and the acceleration and the expansion of the universe with dark energy. And it's going to do that by surveying galaxies and supernovae. So galaxies are, like our Milky Way, agglomeration of stars and gas and dust. And supernovae are explosions of a particular, there's multiple kinds of supernovae, but the one that Roman focuses on are an explosion of what's called a white dwarf, which is a remnant core of a star like the sun and builds up mass from a donor star. It gets too massive and it explodes as a supernova. And by observing galaxies and supernovae using multiple techniques, we can place constraints on the acceleration of the universe over time at different epochs in time and sort of map out if the acceleration has changed, is it a constant? And those very high precision measurements that we can only do from space, we can't do them from the ground because things like the atmosphere and other uncertainties get in the way. We need very high precision measurements with very high sensitivity is what Roman will deliver, which is why it's a new next step in the progression of measuring, these fundamental parameters of our universe. The other thing Roman is doing is looking for exoplanets. It has an exoplanet component. It does that with the wide field imaging camera, which is what it uses to do the supernova and galaxy science. And it does it via what's called the microlensing method, which is a very sort of ingenious technique where you look at a part of the sky where there's lots and lots of stars, millions and millions of stars, like into the sort of toward the center of our galaxy. And there's stars in the background. And then there's stars that we see that pass in front of those stars just because of random motion of stars in the galaxy. And because the star in the foreground has a gravitational field, like all massive objects, that gravity bends the light of the background star and acts as a lens. And it makes that background star get brighter over time. And if that star in the foreground also has a planet in orbit around it that's oriented in the right way, the mass from the planet will cause a little blip in the brightness of the background star. So you can imagine if it's just a star and a star, the brightness is pretty flat and it goes up and it peaks and it comes back down. If it's a star and a planet, the brightness is pretty flat, it goes up, maybe it reaches a peak, and then it has a spike, and then it comes back down. And that spike is consistent with that planet. And so Roman will detect planets in this way by looking and doing a survey over time into the galactic bulge in our galaxy, where there's a very high density star field. It also carries another instrument called the Coronagraph, which is a technology development instrument that's pioneering new technology that we're going to need to really study in detail exoplanets via direct imaging. So we're not talking about a transit detection where we see it cross in front of the star, not talking about microlensing where we see this blip in the light curve via the gravitational lensing method. But we're literally using an advanced optical system to block out the light of the star, reduce the glare, draw out the faint planet nearby the star, and really like take a picture of the planet. And so Roman has this instrument called the Coronagraphic instrument that's going to be pioneering new technology to make this happen. And it will have the capability of doing some science, although the science will come after the technology demonstration to show the technology works. And so it's going to be an amazing mission. First, big wide field telescope with this kind of capability, and also pioneering these new technologies to really do exquisite imaging and measurements of planets to look directly sort of at the planet and measure its atmosphere, et cetera.
I've long considered the moon landing to be the greatest accomplishment of man. I'm sure you hear that all of the time. Mm-hmm. How much more advanced is the technology you just described than what was used to get us to the moon?
Well, I don't know all the details about the sort of engineering that went into the moon landing, but I can give an anecdote, which is the computing system in the lander that took Neil Armstrong and Buzz Aldrin down to the surface of the moon. The sort of power in the computing technology in that lander was less than what's in a typical cell phone. And so, we're talking about really big leaps in technology. But I think that the moon landing back, in the late 60s can really show you that even in the limit of technology, the ingenuity of people is really, really impressive and inspiring. And you make do with what you have. I think we're still sort of still in that situation where we're really trying to push things to the limits all the time. That's part of what's great about working at a place like NASA, because that's kind of what we do, is we figure out what's available and we take it, to the limit to really pioneer new things, build new technologies, learn new things about the universe, about our planet, about the planets in the solar system, about the sun, things like that. That drive continues to this day.
Thank you. Christian, you had another science question. Your IQ is double mine, so it's going to be very different than the type I ask. Why don't you ask your question?
So speaking about the advancement of technology, telescopes have been advanced greatly over the time. So what are the limitations of what we can see in the universe?
That's a super interesting question, and it sort of gets into the question of what is the universe, right? And we have this direct evidence of the Big Bang and the expansion of the universe over time, and because of how we think that the universe came to be via this Big Bang. So what you have to picture is that something happens. We don't know what triggered it, and basically space and time and everything in it at a single point just starts expanding outward. And as soon as it starts expanding, all of that energy, sort of because we're always looking for in physics, we're trying to get to low energy states and try to find equilibria. That expansion and that Big Bang, as we call it, which wasn't really an explosion. It was sort of things popping out and space and time itself expanding outward and everything in there. That has some steps along the way. And one of the things that happens in that progression is the universe begins and it's this hot, very, very hot soup of all this energy and particles. And as it's expanding, it's cooling and things are changing and, atoms form and whatnot. And eventually the expanding universe gets cool enough that electrons can couple to hydrogen nuclei and form atoms. And when that happens, the constant scattering of photons, light particles in that very large expanding cloud of stuff, they don't have to keep scattering anymore because you don't have these free electrons around. Now, I'm not a cosmologist. I'm trying to break this down to the basics of what I know and have read elsewhere and heard from others. But once that happens, those photons can propagate outward into the universe. And we can see the remnants of those photons. We can see that via measurements. We call it the cosmic microwave background. You may have heard of this before. And we can see that as sort of a nearly uniform distribution of light all around us, everywhere we look in space. It's not perfectly uniform. There's very tiny perturbations in the intensity, which corresponds to the temperature. But that's effectively as far back as we can actually see. Because if you try to go further back than that, the whole universe is just this, hot soup of scattering photons that we can't really see individual things inside of. And so if you're looking back, my understanding is that the furthest we can see is that cosmic microwave background that is consistent with when the photons scattered out of that early soup and propagated out into the universe. Now, if you want to say, how far in the other direction can you see? That's a different question, and that has to do with, is the universe finite and things like this? And I'm not enough of an expert to even start to get into that. I can tell you how far back you can see, but the other direction is harder for me to even conceptualize, to be honest.
Yeah, thank you. People often refer NASA as the titans of technology. How can aerospace technology be applied to technology commonly used on Earth? For example, how could space travel benefit normal transportation?
Well, it's a very interesting question, and I could envision some ways space travel could benefit normal transportation, but you could think of right now, if you want to fly in a plane, from where we are in the East Coast of the United States to somewhere in, say, Southeast Asia, it's a very long flight, and the planes travel at a speed that's pretty fast, but it takes a long time to get around our planet. And you can envision that if it's really easy to get into orbit, you can go a lot faster. You can go, up into orbit. If you're in a typical low Earth orbit, it takes you about 90 minutes to orbit the entire Earth. And so if you could get up into orbit and then, travel that distance in orbit and come back down at your destination, re-enter at your destination, if space flight was that routine, right? Like if getting on a rocket, going into orbit, going some fraction of the orbit around the Earth and re-entering at your destination was as routine as getting on a long haul commercial flight, you could imagine how much more quickly we could travel around the planet. And so that's sort of an interesting idea. I don't know if it's super practical, but it's interesting, if getting launched into orbit and orbiting a little bit and coming back down were that easy. So that's one way that, our current sort of step in the direction of easier access to space via commercial launch capability, where it used to sort of be the role of, governments had the technology and the funding to launch rockets and put satellites and people into space. And we're partnering now with commercial entities to take over that aspect of it and provide their own launch capability, which can be done cheaper and faster than it used to be. And we're heading in the direction of more easy access to space, not only for satellites, but also for humans. And so we can think of things like that. And another, just general anecdote about how has technology that's been developed for space benefited everyone. I will say that, something that I like to think about, because it's close to the kind of research I do, is we use these advanced detectors, to detect the light coming from stars and galaxies, et cetera. And those detectors carry the same exact technology at the root level of the camera in everybody's cell phone. And so, that technology development for, astronomy leading into low-cost, mass-produced, high-sensitivity detectors is what allows us to have this conversation via the camera on our computers, because those cameras carry very similar technology as to what was developed effectively going back to about the 1980s to do astronomical observations using electronic technology as opposed to photographic plates. We literally used to have big glass plates with a photographic emulsion. You'd expose it, behind a telescope, and then you'd have to go get it developed and you'd see what you captured. but now everything's digital. And part of that push for that technology has led to mass consumer products that carry these same kind of detectors, which have, I think, really connected us all more, especially in this last year of the pandemic. Doing telecons has been really, really, really important, and that kind of technology has allowed that.
Definitely. Yeah, we only have a couple of more questions for you. I don't know how practical this next one is, but Christian, why don't you ask about Tony Stark? Because I thought that was an interesting question.
Yeah, the question is, could technology portrayed in movies be replicated in real life? For example, Tony Stark's nanotechnology in Infinity War.
So I will say that things like nanotechnology are real technology. There are people who dedicate their lives to the research and development of nanotechnology. The idea of having something as advanced as, you push a button and these particles pour out of some container and form an ultra advanced suit around you as a person to protect you from whatever it may be and give you strength and other capabilities. I don't think we're there yet, but nanotechnology is a real thing, and people are really investing in it and trying to make it happen. And for example, I don't work in nanotechnology. I don't do those things, but I know, just being in the scientific community, that there's a lot of ideas about using nanotechnology for medical purposes, for drug delivery, and for internal sort of illness detection and things like that. So I think we're a long way off from the kind of, to go back to your example of the nanotechnology in Tony Stark's Iron Man suit. But it is a real research field, and there are people who are working on using that technology to better people's lives, and push it in that direction.
Thank you.
I could also say some things about other technology in movies, but we have finite time, so we can go on to other questions.
Yeah. We only have two more quick ones, and then we can all go have dinner.
Yep.
And again, we really do appreciate it. Go ahead. Where are you taking us next?
So this one's more of like a general science question I've been thinking about for a while. So why do you think scientists are struggling to create a theory that links quantum mechanics with general relativity?
So this is a very outstanding question in physics and astrophysics in general. And I am not a person who studies any of the things that are related to this, but I can tell you what I do know. So quantum mechanics is, in general, a field that governs what happens at the very small scale. So, for example, the weak nuclear force, which is one of the four forces in nature that is studied in that field, governs radioactivity and things like that. It operates in relatively small scale. The strong nuclear force is even stronger and operates on even smaller scale, and is effectively what holds the nuclei of atoms together. And so that's sort of, quantum mechanics is a study of things at that very, very small scale, the constituents of atoms, and atoms themselves, and how is all that put together in a rigorous and predictable way. And the forces involved are operating at very small scale. Gravity is a very weak force. It's extremely weak compared to those nuclear forces I described in the realm of quantum mechanics. But it operates on very large scale. So this reconciliation between things that are very, very strong but operate on very tiny scale, with things that are very, very big but have very weak sort of connections, like gravity. I mean, the Earth is very, very big and has strong gravity, but I can pick up my phone without problem because gravity is strong, but it's not that strong. If it was as strong as the strong nuclear force, I would never be able to pick up my phone. I wouldn't be able to move. I'd be crushed against the surface of the planet. And so that reconciliation is part of the problem. It's a problem of scale. How do you connect something that's really weak and operates at huge scale to something that's really, really strong and operates at tiny scale? And the one place where this all sort of comes together is another very interesting topic in astrophysics, which is black holes. So a black hole is a place where there's extremely strong gravity, so strong that the other forces basically break down and don't work anymore. And so I don't know the outlook on this, but I do know that we're learning a lot more about black holes right now with the discovery of gravitational waves, which happened, in 2015. And gravitational waves are super interesting, and they're going to teach us new things about how gravity works and propagates. And if we can understand black holes, I think that that might be a place where this connection can start to be made, because a black hole is the kind of place where gravity is operating in a way that it doesn't usually operate. It's so concentrated and it's so strong that it effectively is overpowering these other forces. And I think that that's an interesting, sort of paradigm and place to dig in and think about what does that mean. And another place that we at least have theoretical evidence, perhaps observational that I'm not aware of, evidence that those other forces and gravity were linked together was in the very, very early universe. Very, very shortly after the Big Bang, when the universe was small and compact and extremely hot and energetic. All those forces in nature somehow came out of that. And so they must have all been bound up together in one way or another. But we simply can't replicate those conditions on our planet. It's too much energy, too much density. We can't get there. Not to say we never can, but right now we can't. And so, to really put those two things, those two very different things, the forces that govern quantum mechanics and the force of gravity that governs things at very large scale over very large distances, to put them together, it seems to me you need a very extreme scenario, like a black hole, which is quite extreme, or the very early universe, which is also extreme. And so there are people thinking about this and trying, as you mentioned. We haven't got there yet, but that's what I know, and that's, I guess, what I'll say I'm comfortable saying about it, given my limited knowledge.
The unknown can be scary. Christian, ask the question up here, and then we'll be on our way.
All right. So this is the last question. What's the most frightening fact you know about the universe?
Interesting. The most frightening fact I know about the universe. Well, something that I think is unsettling about the universe is that it is just so big. And, we as humans on this planet, I mean, we live out our lives, we go about our daily business, we have our friends, family, loved ones, etc. And, we have this experience here on this planet, and out there in the universe, there's an enormous amount of stuff going on that we just don't really know about. We don't have access to because it's hard to measure, or it's too far away, or all those things. And so just the enormity of it all, I think, is pretty unsettling. But it's also inspiring to me, because we are sort of these small living things on this planet, the third rock from the sun, as people have referred to it. And we can look out there, and we can develop technology, and we can use our brains and work together toward answering these questions just from our small vantage point here. And so the universe is huge. It's a scary place with a lot of extreme stuff going on. But we here on our planet, in our own way, can learn about it, and we can sort of understand it and understand our place in it. And I think that that's, this sort of contrast between how big and imposing the universe is, but how, we're still able to make some sense of it in our own way.
Thank you so much. We know you're busy and important, and this was a true highlight for both of us. I really appreciate you meeting with Christian and me today. And Christian, do you want to say the final thought before we go?
Well, again, thank you. Thank you for
welcome.
being able to do this interview. It means a lot. Thank you.
Yeah, it's been super fun. I'm really happy to chat with the two of you. Thank you so much for the really interesting and sort of provocative questions. And I hope that my descriptions and my answers were acceptable and helpful. And I hope that everybody finds something that they like in the interview.
I'm leaving the interview a little bit smarter than I was when I entered it. So thank you for what you did. I really appreciate it.
It's been a pleasure. Thank you so much.